Welcome to Dr. Nakamura's lecture series on bridge engineering, number A-7. Chapter 9, Truss Bridge. A truss bridge consists of triangles which are strong and stable. Although the idea of truss bridge was already known in the Roman era, they were not widely built until the 18th century when steel is available. Its structural form is simple and clear. Each member is light and construction is easy. The member force is axial, tensile, and compressive force. At the connection of members, secondary bending moment occurs. 9.1 Types of truss bridges. There are many types of truss bridges with different arrangement and shapes of triangles. Some of them are illustrated here. Warren truss and Warren truss with vertical struts is widely used. Pratt truss and Howe truss have the diagonals arranged symmetrical over the span center. K-truss are often used for towers. These are some interesting truss structures. A is the 4th Railway Bridge, B the Tokyo Gate Bridge, and C Tokyo Skytree under construction. These are interesting small truss bridges. A is a footbridge which has a curved shape. B shows the water pipe bridge, which consists of three-dimensional truss planes. I show you typical erection methods of truss bridge. This is the large block erection method using a floating crane. This is the cantilever erection method. Members are connected one by one with a traveler crane. Warren truss is widely used. For the simply supported Warren truss bridge, the upper chord is in compression, the lower chord is in tension, the diagonal members are in tension and compression in turn. Tension member in blue, compression member in yellow. Howe truss, the diagonal members are in compression, which is suitable for timber bridges. Pratt truss, the diagonal members are in tension, which is suitable for steel bridges. 9.2 Structural forms of truss bridge. Please look at the two illustrations. A truss plane consists of the upper chord, the lower chord, and diagonal member, which resist vertical forces. Lateral forces, such as winds and earthquakes, are resisted by the lateral bracing, which also consists of truss members. The lateral forces twist the whole truss structure, which is restrained by the portal bracing at the ends and the cross frames. The connection points of truss members are called node, which is assumed a pin or hinge joint with free rotation for the bridge analysis. Therefore, the truss members only take axial forces. However, the truss members are rigidly connected together with gussets, and a local bending occurs, resulting in bending stresses, which are called secondary bending stress. 9.3 Design of truss members. In general, the truss height over the length ratio H over L is 1/6 to 1/10 for the simple span and 1/10 to 1/11 for the continuous span. Suppose the truss bridge is subjected to vertical loads. We place the truss bridge as a beam. Upper and lower chords take bending moment, and diagonal members take shear force. 9.3.1 Calculation of truss member forces. First, the maximum and minimum member forces due to the design load must be obtained to verify the safety of cross-sections. The influence line analysis is commonly applied for this purpose. An example of this influence line analysis is shown with this Warren truss bridge. The influence lines of the upper chord U1, the lower chord L1, the diagonal D1 and D2 are obtained by these equations and shown here. (9.3.2) Cross-section of the truss members. The truss members are subjected to axial compression or tensile forces, and their cross-section are box section for the upper and lower chords as shown in figures below. For diagonals, the cross-section is H-section for tension members and box section for compression members. Flanges and webs are connected by the fillet welding, which transfers the shear force. Structural detail of node is illustrated here. Diaphragms are arranged at the node to prevent deformations of cross-sections. The diagonal members are connected to the lower chord through the gusset plates. The gusset plate is welded to the webs of the lower and the upper chord, or a part of the web forms the gusset plate. The diagonal member is inserted between the right and left gusset plates and bolted together. Verification of truss members. As it was explained, the box sections or H-shaped sections are commonly used. Steel plates were welded to form these sections. For a box section, hand holes are necessary to set high-tension bolts for connection at the nose. This is the verification equation for the limit state 3. For the tensile member, the net cross-sectional area is applied. The bolt holes do not resist tension and should be deleted. For the compressive members, the gross cross-sectional area can be used. The effect of buckling should be considered. Therefore, the minimum slenderness ratio L/R is specified 120 for compression members. Exercise 9.1 Design of Warren truss. Verify the upper chord member U3 of a Warren truss bridge shown here. Note that the design dead load is D equal 45 kN per meter, and the design live load is P1 equal 40 kN per meter and P2 equal 10 kN per meter. Yield strength of steel is 355 Newton per square millimeters. First, calculation of member force using the influence line of U3, which is shown here. We have to find a critical position for P1 so that it produces the maximum value which occurs at y2 equal y3. Then we can get A1 and A2. A1 is triangle ABF and A2 is pentagon DEFGH. So the member forces due to dead load and live loads are calculated like this. The upper chord U3 is a box section which consists of an upper flange, two webs, and a lower flange. Its sectional properties, cross-sectional area, moment of inertia, are calculated in this way. Remind you that the position of neutral axis must be found, and the slenderness ratio should be less than 120. Then we can calculate the stress and the limit value. The stress is within the limit value and satisfies the limit state 3. That's all for this lecture. See you next lecture.